Okay, hold on, let's see. I'm quite sure many theories are approximations. Yes, all theories are approximations. Like with anything, like a physicist has the benefit of studying the coolest science and not the lamest science, which would be chemistry. A physicist has the benefit of working in an environment where they can make certain approximations. So for example, you can say, oh, here's my particle, and I'm way over here observing this particle, and so I'm going to treat this particle as though it's a point source. And so you say, oh, this particle is a dot with some mass, like in infinite density, but it's a dot of some mass, and then I'm going to calculate the forces. And that alone is already an approximation. So for example, it's like saying the Earth is round. The Earth is not round. You heard it here first. So the Earth is not round. It is an oblate spheroid. And so, but when you are calculating, what is the gravitational field of the Earth out at the orbit of the Moon or something farther away, then as long as the deviation from roundness of the Earth is not important, or does not introduce an error that is larger than the tolerance that you've specified for your calculation, then you can use the Earth as a round, like a point source round object without any trouble. However, if you're worried about, how is this satellite going to tumble because of the changing quadrupole moment of blah, 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 then you actually have to worry about the fact that gravitationally, the Earth is shaped like it's not even an oblate spheroid, it's kind of a pear-shaped spheroid. The Earth is shaped like this, and this is going to give off a gravitational field that is different from the gravitational field that you get from a point source. So a point source gravitational field is spherically symmetric. This shaped gravitational field is going to have some weird distortions, and it's not until you get really, really far away that it looks spherically symmetric. And so when you're studying these things, you're going to say, I'm going to make the approximation that, and then use whatever that approximation is. So physics has the benefit of being able to make those kinds of approximations. Well, we're going to assume that the energy is really low, and therefore this. Or we're going to assume that the energy is really high, and therefore this. A perfect example of that, a shape that looks like, I don't know, like this. Thank you for that follow. You have a shape that looks like this. At a great distance, it looks like, way out here, the gravitational field will basically be spherically symmetric. But as you get closer to it, the gravitational field will be distorted by that peanut-shaped object. And so here's your lines of constant gravitational potential energy are going to look like that. Oh, that's kind of ugly, but you can use your imagination. And so when you're way out here, it looks like a point source. And as you get closer and closer, you'll notice that the gravitational field gets distorted. And you can use that distortion in the gravitational field to infer the density distribution of the object that you may or may not be able to see. So for example, if you have a planet like Jupiter, so Jupiter has some structure in its interior. It has different layers. Those different layers are going to be oblate at different rates because of the rotation that you have and the tensile strength or whatever. Thank you for that follow. And so you have a planet. It has some unique structure, how the mass is distributed. You can't see it, and no one that I know of would want to volunteer to see it, jump into Jupiter and die after a few seconds of exposure to the high winds. And so the question is, how can you understand what Jupiter looks like in its interior without actually going into the interior? And the answer is you fly around Jupiter and you look at how a spacecraft accelerates in Jupiter's gravitational field, and you reconstruct from, say, the shape of Jupiter's gravitational field at different elevations and around different trajectories. And then you use that to infer the mass distribution of the material inside Jupiter. And once you get the mass information at a certain size, then that gives you the density profile, and then you can reconstruct, for example, whether Jupiter has a core. So it wasn't known whether or not Jupiter has a core till, when did I go to that conference? Would have been 2016, I think. And so it was just before then. So it was like early 2016, 2015 is when we demonstrated definitively that Jupiter has a core. So now we know Jupiter has a core. But before 5 years ago, we weren't sure if Jupiter had a core or not. It was possible to have a model of Jupiter that did not involve having a rocky core. That's not true anymore. And it was done by probing the gravitational field around Jupiter. Not sure exactly how to do that. Didn't a whole bunch of physicists try to draw up the most likely theories to disprove GR, remembering reading about that? Well, I mean, physicists are always trying to disprove GR, because as soon as you disprove GR, then you win, right? You've discovered new physics. And so, I was on a gravity experiment specifically to look for violations of the predictions of gravity. And if you were to discover it, then you throw your arms up in triumph. You get a new physics building for your department, and then your name goes down in history. So physicists are always trying to disprove GR. It's just hard to do because it works. And so the way that you do it, you have to make very sensitive measurements on very close scales. Normally, there are two different ways of kind of disproving GR if you want to disprove it. It doesn't really disprove it. It's just that you demonstrate that there needs to be, the physics needs to be more general than general relativity is able to provide. But the way that we would interpret, depending on the nature of the violation of general relativity, the way we would interpret it is different. So if we were to do these torsion pendulum experiments, so you have a thing like this, and you have different objects, and you have some source mass, and you're saying how does this pendulum twist in the presence of this source mass? You may be trying a laser beam off of it. So these kinds of torsion pendulum experiments, you would, if you were to see a deviation from general relativity, so general relativity has certain fundamental principles. The way that this would be interpreted today is not that you ruined general relativity, but rather that there's a new force, and that new force is coupling in some different way to the different sides of this pendulum. And it could be that you have something that causes a deviation from the inverse square law, so that the gravitational potential does not actually go as 1 over r, but actually has some other component to it. Maybe there's some other force that's acting and so in which case you get a Yukawa potential that would look like something like this. And depending on the mass of that particle that couples, you have this exponential term. So you would describe it as a new force. So if you detected it in some kind of torsion pendulum thing like this, you would describe what you found as a new force and not as like something wrong with general relativity.